section 9.4. There are 2 more tests. We have been through section 9.2 and 9.3. There were 2 tests in each of those. We're not going to say what they are or how they work, but we are going to list through them really quickly. What's the first test that we could look at? And turn. Don't say what it is. Just think about it and be like, that's a thing. Okay, what's another one? Don't say it out loud, but that's a thing too. What's another one? Integral. There's some things that need to be true for that, right? And then what's the last one? Yeah. But what if something doesn't fall into any of those categories? Let me give you an example. Ready? Okay. What if I was to give you something like, ready? And term, yes or no? Don't say why, just yes or no. Doesn't work, right? Doesn't help. Geo, yes or no? No, nothing different. Integral test. Maybe, except what would have been real nice? Wouldn't that have been real nice? Because then we could have done a U sub, right? Because U would have been, and then DU would have been. But it's not there. What else would have been real nice? Why would that have been real nice? Arctan with U being and squared with a DU of, but guess what's not there? Man, I made that a better example than I even thought. Not integral test. Because how would you integrate it? Maybe some of you are like parts, but in parts, we never want an algebraic with an algebraic if we can avoid it. Because it could just get worse and worse. Because I could derive this, but then it's going to be a squared and a cubed and it's getting worse. I can't dv it. So then, what's the last one of the 4 that we know? But is it a p-series? No. But can I compare it to a p-series? What if it's close to, but not quite? Ooh. Do you know how for the integral test we would say, don't worry, I'm not giving anything away. Consider somebody. For these ones, we're going to say compare to. But here's my question. How does this compare? Smaller. Why is it smaller? Because if it was just that over that, right? Wouldn't that be 1 over n squared? Sure. But then, it's always going to be just a little bit bigger. Wait, what's a little bit bigger? Denominator. And if the denominator is a little bit bigger, what's true about the overall magnitude? Smaller. So can I say that this is smaller to this, which is, are any of you looking at that test yet? Bigger. What does that say about what conclusion can be made if I know what the bigger does? If the bigger converges, then what can I say? Smaller. Does the bigger converge? P series, and P is. Okay, so all that to say. Okay. It's okay. David says it in the way he couldn't see anyway. Okay, so coming back. If the bigger converges, the smaller converges too. Now, some of you might be like, why is there a BC and an SD? Like, what the heck are you trying to do? Okay, ready? Love my smart board. Okay, so if the Oh, hey there. Good morning. Okay. What I just asked a second ago was, what can we say from the bigger? Okay? The only thing that we can say from the bigger, or the only thing that we can prove from the bigger, is convergence. And here's a struggle. What if the bigger had diverged? We know nothing. Oh, I know, right? I know. No. But AJ, thank you. That's perfect. Because remember the nth term? How sometimes we know nothing and sometimes we know everything? And we have to be really careful, because if we know nothing, we can't say something, or else we're in trouble, right? But if we can say something, oh my goodness, say it and be done. There's a life lesson somewhere in there. But coming back, bigger. If the bigger converges, the smaller converges. But if the bigger diverges, we know nothing. What do you think that means about this? If the smaller diverges, the bigger diverges. But if the smaller converges, we know. Okay. How does this make sense? Can I have you guys think about the squeeze theorem? It's okay. Go ahead and grow. Okay. Squeeze theorem. With the squeeze theorem, I want you guys to think about a standard like number line. Just as far as having some sort of context to magnitudes, greatness. Okay, a number line measures greatness of positive and negative numbers. Okay. The farther you are from the zero, the greater your magnitude, whether your magnitude absolute value, right? How muchness, vectors, you could get into physics, so let's stop. We can even talk about absolute value of complex numbers and how the absolute value, the magnitude of complex numbers is also vector math, but right, Brian? We can talk about how I had a college kid text me, or she was on her Insta story, and it was her having to remember vectors from her honors pre-cal class 3 years ago, and she's in kinesiology right now. Oh, that's the class. I could talk about my other kid who's in grad school doing some advanced statistics course who emailed me or Facebook messaged me and was like, man, I wish I kept my forever cards because we're doing second derivatives and logarithms right now. So I sent her a link to the forever cards, and she was like, yeah. But anyway, so you never knew when calculus would come back. Stats, who knew? That's not like a math major, that's like business, right? Or stats is necessary for any like future in science. I'm not sure that level of stats, but I'm pretty sure she's in grad school. And then the other one, kinesiology, poor kid, who would have thought? It's okay, her brother's in honors pre-cal. I was like, have him tutor you right now because he just learned it. Anyway, came in this morning, he's like, I helped her. I was like, yeah, you did. Anyway, okay, coming back, number line, magnitude. Okay, can we pretend this is 0? And can we pretend that I am a BC, bigger converging? Okay, I'm a smaller. Cool. Where would the bigger be on the number line? Just to visualize. I'm on the positive side, right? I'm smaller. Bigger's over here. Okay? If the bigger converges. Pause. Abby, come here. This will be fun.
Abby.
This is the 0. No, Abby's the bigger.
Yeah. Wow.
You thought that was Mommy Five Hour, right? There we go. Okay, I'm the smaller on the number line. True? Doesn't matter how messy I look or how big I look. I'm smaller in what I'm worth or what I'm. I'm smaller. Okay, bigger. Okay, if she's converging, is she going to infinity or is she coming to some sort of constant? All right, converge. Come on, bigger. Converge. 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 I don't know where we're converging to, but what's going to happen to me? I get squeezed into converging. Can I go to infinity if this bigger is converging? No. Now, wait a minute. What if bigger diverged? What am I doing? Could I be diverging too? Could I be converging? Does anybody know? So what's the only thing that we can tell from a bigger? Convergence, because then I get squished. Okay. Good? Okay. Now, wait a minute. What's the next case? She's the unknown. The bigger is the unknown. The smaller is the one that you know. Okay? So, what if the smaller is converging? Do we know what she's doing? Could she be diverging? Could she be converging? Yeah, I don't know. I'm just doing that. But what if the smaller diverges? She has to diverge with me, right? Baby, stop. She's a little dramatic. Okay. Everybody happy?
Happy.
Okay. Does that make sense? So does this test always tell me something? But is there someone that I don't know? But if only I could compare two, I might know. Does that make sense? Now, the struggle between this, which is called direct comparison, and the other one, you're welcome, which is called limit comparison, is that direct comparison, I need to know directly something that's always bigger than to be able to make this conclusion for convergence, or always smaller than to make this conclusion for divergence. Because if it's not always bigger or always smaller, the whole thing breaks down. If it's only sometimes bigger, well, she could have jumped right over me, or if I was only sometimes smaller, I could jump right over her. But if always bigger or always smaller, then I can make these conclusions. So, what's the BCSD thing all about?
Bigger converges, smaller divergence.
Bigger can only tell me convergence, smaller can only tell me divergence. What's the nice thing? What calculus are we in this year?
BCC.
Oh, nice. Bigger is only convergence. So then smaller is the other one, divergence. Sound good? Okay. Now to that end, you guys saw the one that wasn't quite a P-series, but if I could compare it to a P-series, oh, that's easy. That's nice. I can say we converge it, right? So here we go. Squeeze in versus push out. You saw Abby squeeze me in. That was a bigger converging, squeezing in a smaller. Pushing out would be the smaller diverging, pushing out the bigger one. Sometimes the hardest thing in this one is finding one always bigger or finding one always smaller. Just a quick little peek ahead to the AP. You guys know how, and you should know. In some questions, isn't the AP very explicit about like, hey, by the way, you have an F, you have a G, and the F is always bigger than the G. It can totally tell you it's bigger. Or the F is always smaller than the G. Oh, it's telling me smaller. This test could come up with them just telling you it's true. But to be honest, if they're not telling you if it's true, and if it's not something similar to a P-series, it probably isn't the best test to use. Do you see what this little note says? This is kind of like more like a last resort. Other ones are easier to apply, usually. This one, integrating it, you should not have gone down a rabbit hole trying to do something ridiculous for convergence with an integral. It's not meant to be that hard. Doesn't mean that some of the integrals might not have been hard on Friday. But in theory, the integral test might be easier to apply if possible than some of these, or than the comparison test. And what's the other thing that hopefully you guys can see? This only works with what kind of terms? Because imagine if you have positives and negatives, I don't know, always bigger, always smaller, all of a sudden it's jumping all over the place and it's going to be way more complicated. Okay? So, let's look at some examples. Let me show this to you because this is super helpful, not only for the direct comparison test, but also for the integral test. I've mentioned to you guys that it's very possible we're going to see some series where the conditions are not met for certain tests at the very beginning, but if we could just separate some of those terms off on their own, like A1 plus A2 plus, okay, the infinite series from 3 to infinity. All I need is to know the convergence or divergence of the infinite, and then I can add the finite, and I'll know. Divergent plus finite, divergent. Convergent plus finite is convergent. I don't necessarily need the entire series from the very first term to the very last term to meet conditions. But I do need it to eventually meet the conditions for forever, or else I'm in trouble. Meaning, I could have a series that starts off a little bit above and then eventually goes below, and as long as I separate, okay, it's smaller for forever, even though it was bigger for a couple terms. You might see me doing a little bit of having to split up, and so that means that you would have to split up as well for your proof to be seamless. Otherwise, if you say something like, hey, the bigger converges, and it wasn't bigger to begin with, that doesn't really help unless you actually show the part that's converging and how that applies to the whole. That's kind of what's going on here. We'll come back to it if we need to, but basically, if I can split it up, if I need to split it up in order to have it meet the test, I will. Okay. Let's start off, and we're just going to go slow and steady, okay? Because some of these are really easy, and some of them are a little bit more tricky. So, number one. Oh, come on. Okay. Number one. What does it look a lot like? Nth term, we know nothing. P series would need to be an N to a P. This is a P to an N. Geo. Looks a lot like a geo, but what's going to mess up the geo? Feels kind of like that one. The plus one. It was a P series, but a plus one, right? So what could we try to compare this to? Okay. Now pause. We need to, before we keep going, some of you are like, oh, hey, it's geo, and it's this because of this, and okay, cool. But we need to know if it's bigger or smaller to know if that's even going to help us. Does that make sense? Okay, so bigger or smaller? Bigger because its denominator is bigger, right? Smaller value. Okay, cool. So we can say always greater than or equal to. And you could try plugging in if you needed to. Plugging in 1. So that's going to be 1 over 2 to the 1. So 1/2 plus 1 is 1/3, whereas this one's 1/2. You could plug in 2. That's going to be 1/5, whereas this one's just 1/4. This guy's always going to be bigger than. That's P. BC, right? BC, since this bigger converges. You realize why I'm being cryptic, but does that make sense? Since this one is bigger, and since the bigger converges, and I put a little quick then smaller. And technically, I guess it probably would be a better placement for the parenthesis to be there, because direct comparison has nothing to do with geo or any other convergence test. It's its own thing. So since the bigger converges, this is the direct comparison test. My parenthesis would be like, how is it? If I needed to go through that, I would go ahead and state which test I'm using and why. Now, because the bigger is a geo, can I say what this converges to? No. Now I can say what it's bounded by. I can say what this one is converging to by my formula for the if I could. Okay. And I know that this one's going to have to be smaller than that because it's bounded by that, but I'm not exactly sure what. So even though there's a geo series involved, I'm not going to be able to totally say what that's going to. I could just say what it's bounded by, but that's later for approximation in a totally different, to be honest, chapter. That's in our chapter 10. So. BC, got him. What about this guy? If it was times, it'd be so much nicer. Oh, it would just be P series if it was times. Okay, well. You can try to do integral test, but Ninth term, we know nothing. Geo, yeah. P's, no. Can I show you a couple different options to think about? First of all, we can throw that guy out and be like, okay, he doesn't really make a difference. Because what I'm trying to figure out is the convergence or divergence of this guy, and the 3 doesn't really have a bearing. Okay? 3 times divergent would be divergent, 3 times convergent would be convergent. So I can take a moment and just look at 1 over n plus square root n. Let me point you in 2 different possible directions. What if they were the same, or what if they were the same? Okay. This would be, and this would be, what's what? Bigger or smaller? Why smaller? How do you know that? You think about y equals x or y equals n versus square root of. Which one has a smaller magnitude? This guy, right? Smaller denominators, bigger numbers. Good? Bigger denominators, smaller numbers. True? So smaller. And I can talk about his convergence, divergence in a second. Small. What about this guy? Right? He's bigger, which means, wait, his denominator is bigger. His denominator is smaller. So how does that compare with the entire? Okay. Now, what does he do? Converge or diverge? Or we could say, right? But what about this one? Good? Which one helps me? BD? No. It's BC. This one would tell me nothing. This one would be Abby going to infinity and me, who knows. This one is me going to infinity and Abby gets pushed. Does that make sense? SD, that's something I can use. BD, nothing. I know nothing. Does that make sense? But do you see how, like, your brain could have gone either direction? That is a comparison. That is a comparison. Only one tells me something helpful. So there are going to be times when you guys make a comparison, and then you're like, oh, yeah. Oh, it's not BC or SD. If it's not bigger converging or smaller diverging, you know nothing. You have to go back to the beginning and try something else. Kind of annoying. Does it make sense how this one proves? So I could go ahead and say, okay, so I want to use this one. So compared to, just throw the 3 over. That's okay, the 3 can come in front. So 3 over, which is always smaller than. You could try throwing in the first few terms just to make sure, because that'd be 3 over 2, and that'd be 3 over 2. Ooh. They're the same? Okay, for a little bit. The squeeze theorem, less than or equal to, greater than or equal to, that was okay. It still squeezed if it was or equal to. But if I plug in 2, now I have 2 plus root 2 versus 4. Okay, at that point, this guy is now bigger. Thank you. But I didn't have a problem where my smaller, bigger switched. It was like, okay, they were equal at first, but then they start to go ahead and go different directions as far as different strengths. So I can have that guy who's always smaller than this guy. Since the smaller diverges How about this guy? Oh, side goes positive and negative. Can't use the test. It's not just sine. Sine squared. What are positives and negatives squared? Okay, so pass the test. What do you guys want to compare to? Why not? It's a lot like the first one, right? But you guys tell me, greater than or less than? But why? What's the highest sine can be? And what's 1 squared? So what's sine maximized by? 1. But what does sine do? Fluctuates, oscillates, right? So what's 1/2 squared? 1/4. What's root 2 over 2, which is 1 over root 2? That's 1/2 when you square it, right? So you're going to have sine going. Now, that's the numerator, though. So careful. When the numerator is smaller, isn't the whole thing smaller? Okay. So 1 is the, now, greater than or equal to, because sometimes sine is 1. Greater than or equal to, sometimes sine is 1. Now, hold on, wait a minute. If it's sine of 1, sine of 2, sine of 3, sine of 4, that's never actually going to be 1, because sine is only 1 at pi over 2, which is a weird, awkward decimal. So technically, I could say not even or equal to, because I don't have a pi over 2 coming from one of those integers. But either way. Is it good that that guy's bigger? Yes. Because what did I already say about this guy? So bigger converges. It's the exact same by geo, by direct comparison. From up above. Is that good? Okay. But do you guys notice, like, where is this or how is this going to get messy? You have to know if it's bigger or you have to know if it's smaller in order to be able to make the comparison. And sometimes there are multiple comparisons that would be made, one that tells us nothing and one that might tell us everything. It can get a little frustrating. It can definitely get a little frustrating. Oh, the brownie knocked him out. Okay. This isn't the second test. This isn't the second test. This is a special case or a special type of series that technically in our parting C, Moses parting the C. Our parting C are different, 9 different, 10 different convergence tests. This technically has its own letter, even though it doesn't have its own test in our book, or our other book, maybe I should say. So, as you guys are writing, parting C. This first one is P-series. Telescoping. Integral test. And term test. Geoseries test. You see how close we are? Wait a minute. Didn't we just do direct comparison? There's no D.
Comparison.
So guess what? There are actually 2 tests here. There's both direct, that's the one we just saw, and limit. Ooh, there's 2 in 1, that's mean. And guess what? There's actually a, so we have a few more. There's ratio root test, root ratio, whichever you want to do it. So it's parting C. There's ratio root test, and then comparison. There are comparison tests or comparisons that can be made. Alternating series, ooh, we can finally deal with one that goes back and forth and back and forth and back and forth. But you guys see how we're pretty close, right? Anyway, telescoping has its own. Telescoping has its own. Here's the dilemma. Telescoping ones are usually hidden. The way I've written it out, though, it's definitely not hidden here. They're usually hidden, but the way I've written it out. It's not hidden here. The way that telescoping ones can be hidden sometimes, ready? They're usually hidden by partial fractions. Meaning, you don't usually start with partial fractions, you usually find partial fractions. It's usually just a little polynomial just sitting there. You're like, I don't know what to do with you. But if you only factored and made it a partial fraction, maybe it would be telescoping. Wait, why is telescoping so nice? You got a looking glass. Pirate. You guys know what I'm trying to do, right? Alright, they expand it and then they condense it. Ooh, expanding and condensing like logarithm. But coming back. If this is all expanded, you guys see what happens, right? Could I condense it? Like the fundamental theorem of calculus, f of b minus f of a, which was an infinite sum of different iterations of the mean value thing. Yes. What happens? What am I left with? Now, that's this type of telescoping. There are different types of telescoping, or maybe you're left with the first and the third, but everybody else cancels. Or maybe you're left with the first and the second and the fourth, and everything else cancels. It depends. It depends on the partial fraction. It depends on how the series works. Telescoping is just the idea of a lot of in-between, or the infinite in-between are canceled, and you're only left with. Sometimes you're left with this guy. Sometimes you're left with that guy. Sometimes every other cancels out. It can be different. They're not all like this, which is why, okay, this is good as a forever card, but this guy, to be honest, not super helpful beyond you realizing, okay, you're left with something. You're left with something finite, see, or something similar. I had to add that in because it's like, okay, it's not always exactly the first and the last. But the idea is somehow your infinite sum actually ends up being some sort of finite expression, and so you just need to figure out, okay, what's the limit of that? Because the infinite sum, it will keep going, but if we notice a pattern, okay, cool, take that pattern and take the limit to infinity of that pattern, and then ask yourself, does it converge or does it not? Does it converge or does it not? Because if this last guy is diverging, well then forget it. If he's always going to be there, well it's always going to be getting bigger, so therefore, okay, it's going to be diverging. But if he's getting smaller, well then maybe it will be converging. So it's a little bit confusing in the sense of like writing it as a forever card, and it's still important, even though, okay, it's a test, but it's not a test. We try to expand, especially partial fractions. See if things are canceling out. That's why writing out the first few terms can be helpful. What's stuck? What cancels? The nth term, what's stuck? What cancels? Okay, take a limit of that. As I go to infinity, what's going to happen? And I'm sorry that that's kind of ambiguous, but it's because telescoping are kind of ambiguous. I don't know what's going on. Yay, water. Okay, so Victor's excited about something. Although, Victor, you would be proud. Someone in pre-cal.
Victor's drinking soap right now.
What?
The water is soapy.
But in pre-cal, we just started vectors on Friday, or was it Thursday? And I said something like, what do you guys know about vectors? And they were like, Victor. And I was like, never gotten that one before. Anyway, you were more famous than Despicable Me for a second. Anyway, moving on. I just popped into my head. I was like, oh yeah, that happened. It might have been Justin Liu. Okay, so.
Might have been.
I'm trying to think who else was in there. It might have been your brother too.
Yeah,
It might have been Sebastian. I don't remember because he's up here and Justin's back there. But either way, someone was like Victor, and I was like, yep, that works. Okay. Question. Do you think this would have been what was given to you? No. There's. Of course, Sophie water. Wash your mouth out. What's up? Okay, can we just real quick, what would have been here before? It wouldn't have been this. There's no way they would have made it that easy on you. Yeah, it would have been n plus 1 minus n, right? So that would have been just 1 over n squared plus n. Okay, this is what very possibly would have been given to you. And you might have been like, ooh, P series, and maybe a comparison thing, but you realize now this one just had a 1, whereas that one has an n. And if you were to go ahead and compare it to like a 1 over n squared, well, actually, maybe you could have. That would have been lower than, oh no, smaller converging tells me nothing. Oh no, 1 over n squared would have been bigger than. Bigger converging. This one would have worked probably using a direct comparison test. But maybe other ones wouldn't, especially if there's like a minus, then we start to have some really big issues. But coming back. Okay, so this one could be broken down into these ones, and these ones, ooh, let's see what's going on. Okay, so if you zoom in, telescoping. It's not us necessarily doing a comparison, it's just us expanding it and seeing what happens. But for whatever reason, it shows up in this section in this book. Other books might have it as a totally separate piece, but that's all right. Polynomials, partial fractions, let's expand, because otherwise it's like an nth term test tells me nothing. Comparison of the two separate ones, I don't know. If you put them together, maybe we could have done a direct comparison, but if they're separate, you guys could get totally lost on that. But what do you see over here when you start expanding? What's the nth term? I plug in 1, right? I plug in 2, I plug in 3. Don't I get 1 over n? Oh, hey, it's right there, right? What cancels out? Did you guys notice the order? Wait, they're just all canceled out. Hold on. What cancels out first? This cancels out with the first, and that's left, right? So once I get up to here, who's gone? That's gone, and that remains. True? Okay. So if I'm trying to talk about my S of n up to any point is just going to be 1 minus 1 over n plus 1. So up to the 10th, up to the 100th, up to the 1,000. That's always going to happen. The first part of that nth term is going to go away, and that last part's going to be left. So then if this is my S of n, guys, a series converges if its partial sums converge, right? So can't I just go ahead and say, oh, hey, what are you doing, Mr. Partial Sum? For once, I can actually see you. Usually we can't see it. It's just kind of in there somewhere. What's the limit? So, converge or diverge? Converge. Telescoping are a weird one. Might talk a little bit more about it tomorrow, but we'll also get into the limit comparison test. All right, guys, you've seen the direct comparison test. You've seen telescoping. We'll come back tomorrow to keep on talking about comparisons. I think this isn't due until Wednesday? Wednesday. Bye, guys. Happy Monday.